So, hello everybody, my name is Emilio Coppa and I am an assistant professor at Sapienza University of Rome. And the work that I'm presenting today was published at ICSI and then later in an extended version at Computer Security. And this was a collaboration with Luca Borzacchiello, a PhD student at that time, and Camille Demetrescu. Unfortunately, Camille passed away last April, so I would like just to spend a few words on remembering him. So he was a full professor at our university. He was a great researcher. He has done tons of research in algorithms and data structure. And then he moved to program analysis in the last 10, 15 years. And I worked with him when working on program analysis. And he was one of the best teachers that we had. Students loved him. I was one of them. This is in 2007, my first course. And you can see Camille fully immersed in students. I did my bachelor and master thesis with him. And then I had my first paper at KLEE. I was terrified, but it was with me. And then he was also my friend. So I would like just to say that it was an honor for me to work with him, with Camille. Moving to the reason why I'm here, a few years ago, we did a survey on symbolic execution. I was not aware of this technique, and it was love for me. But then soon I realized that it's very hard to implement. So kudos to all the symbolic execution maintainers. And there are many of scalability issues that are very hard to tackle. And then we were also looking at the time at fuzzing. And what we realized is that it's way simpler to implement. Maybe there is a lot of design and tuning, but it is simpler to implement, in my opinion. And it's still quite effective. I mean, if you look at OSFADs, you can clearly see that there are good results with it. And this seems so fair. I mean, I was working with memory models in symbolic execution. It was so hard to debug. When looking at coverage-guided fuzzing, the idea is pretty simple. I believe that you're familiar with it. So you start with a pool of inputs. You pick one input, you apply some mutations, maybe random bit flips, you put some constants in. A lot of random things, some are pretty advanced, but a lot of random things, and then you get a mutated input. So this patched input is then used when running the program. And when running the program, if you see a crash, then you win a lottery. Otherwise, you look for, you track code coverage, and you try to understand if there is a new program behavior. If this is the case, then you put back the input in the queue, and then maybe you repeat this cycle another time by mutating that input. And this is affecting as long as you repeat this cycle millions of times. So one other question is, how can we reduce the number of times that we repeat this cycle? We avoid some useless mutations over the input. And the community has done a lot of work. For instance, they've used tint analysis to understand which bytes are affecting one part of the program. So then they mutate just the bytes that are affecting, for instance, one branch condition. And then the next question, if you're here, is that, okay, maybe we can use something that is more accurate than tint analysis, for instance, symbolic expressions. So we look at the symbolic expressions to understand how to mutate the input. And this is actually exactly what we have taught at that time. So you start with an input, you run the program, you trace the program, you build the symbolic expressions, and then you look at them. You try to understand how the program is working on the input, and you apply the mutations driven by this knowledge. So when I say tracing, I just mean concurrent execution. So you start with an input, you run the program, and the program will follow just one path. Along the path, you build the symbolic expressions. So when you hit a branch, for instance, you take the path constraints and you put in conjunction with the negated branch condition to generate an alternative input. One observation is that when you reach a branch in concurrent execution, you have that the input will satisfy the path constraints by design, otherwise it would be on another path. And then if you want to understand how to mutate the input, you should start looking at the negated branch condition. When you mutate an input that is affecting the negated branch condition, you should do it carefully because the same byte may affect a condition in the path constraints, and then the overall input will not satisfy anymore the overall query. But from fuzzing, we know that in several cases, fuzzers are lucky by just mutating a few bytes, so maybe we are lucky as well. From this, we design FuzzySat. The idea is to have an approximate solver for concolic execution. So when the concolic executor reaches a branch, we have a query, and we try to solve it by mutating the input. And we have two stages. The first stage is the analysis stage, where we look at the symbolic expressions, the structure, we try to understand something, and then we try to solve the query by mutating the input in the reasoning stage. In the analysis stage, removing some details, what we may do is, for instance, to detect which bytes are affecting an expression, if the bytes are used together. We detect constants. This is something that Fuzzing may use in the mutations, which operations are used with these constants. We detect input-to-state relationships. This is a concept from Red Queen, introduced a few years ago. The idea is pretty simple. Most programs will have bytes that are flowing as is, or after a few simple encodings, like reversing the bytes or conversion to an ASCII character inside a branch condition. If you detect these patterns, then you know how to satisfy these expressions. And then we also look for range constraints. So we understand if a byte or group of bytes can assume just a set of values that is restricted. And then we exploit this knowledge when mutating the input. In particular, we start by mutating bytes that are affecting the negated branch condition. So for instance, we exploit input-to-state relationships. We satisfy this condition by reversing somehow the encoding on the pattern. If we see that an expression is involving just a few bytes, and these bytes can assume just a few values, then we perform brute force, basically. Then we look at the condition as a minimization problem. So we apply gradient descent to solve it. And then we use a lot of mutations from FL. We tune them to exploit the knowledge that we had. So for instance, they just work on the bytes that we know that are useful. We look at group bytes, so we try to customize them in our context. However, up to now, what we do is to mutate bytes that are affecting the negated branch condition. But this is not enough in several cases. For instance, here at line 3, we have a branch where the program is testing that the second byte in the input is equal to 1. And we reach this line with an input where the first two bytes are equal to 0. So if you now just focus on this condition and we change the byte, we don't get something that is consistent with the previous path constraints. Because at line 3, we have a condition that is saying that the first byte should be equal to the second byte. So here, what we have to do is to change 2 bytes, but only one is, let's say, affecting the branch condition. So what we do is basically to look at all the conflicting constraints that we have in the path constraints, and then we extend the mutations to other bytes. And this is done with a greedy algorithm. So we fix the values of the bytes that are affecting the negated branch condition if we have found a solution, and then we go back solving other constraints. And this was implemented as a C library. It takes as input basically expressions for C3, the C API, and you can integrate it for this reason in several concolic executors, for instance, QSIM, SimCC, SimQEMU, and then we also developed Symbolic, our concolic executor, and this is available online if you want to play with it. So the first question is, can actually FuzzySat solve queries generated by concolic executors? And we used QSIM, one concolic executor that at that time was pretty effective. We evaluated on 12 programs, different inputs, and we collected a bunch of queries. And then we look how FuzzySat would fare at solving queries compared, for instance, to C3. So a standard SMT solver. And what we saw is that FuzzySat was surprising quite effective. On average, it was even more effective than C3. But of course, in some cases, it was able to solve queries that C3 was not able to solve due to a timeout. In other cases, it was not able to solve a query that C3 was able to solve. And the most important fact is that FuzzySat was way faster than C3 when reasoning on all the queries. So it was 29 times faster. And one of the reasons is that we have a lot of heuristics in the algorithm. So basically it failed fast on several queries where they are unsat, and C3 is spending a lot of time reasoning on them. We also compare FuzzySat with GFS, which is another approximate solver. This is from the research group of Christian Kadar. We were not aware of this project at the beginning, and luckily for us, the design is a bit different. So you have a query, and you encode the query as a C program. So the program will test all the conditions, and then you fuzz the program. So you compile it, and then you use libfuzzer to find a solution. And at the end, what we saw is that FuzzySat was a bit more effective at solving our set of queries, and it was a bit faster. Our intuition behind this is that we were doing the mutations driven by the knowledge that we had, while they were using a standard fuzzer for GFS. And then we tried to understand if basically we just got a slower fuzzer. I mean, FuzzySat maybe is not able to generate interesting inputs compared to what is already generated by traditional fuzzers. So we compare Symbolic, our concurrent executor, with FuzzySat to QSIM using Z3, a standard SMT solver, FL++, one actively maintained fuzzer, and Eclipser, which is a fuzzer that took inspiration from concurrent execution. And what we saw in our setup is that Symbolic with FuzzySat was able to reach higher code coverage in several benchmarks. Some benchmarks, we didn't see a big difference among tools. And then we had one case where FuzzySat was clearly underperforming. So this was on LPNG, and the reason is that this is an approximate solver, and if you get a query that is very, very complex, then heuristics will fail. We know this. Of course, QSIM with Z3 was able to solve this query, so it was able to unlock a part of, to visit a part of the program. So concluding, FuzzySat is not the ultimate solution. There are several limitations that come with it. So for instance, it doesn't support the theory of array, just the theory of bit vector, no floating point. We didn't find a way of alternating an approximate solver like FuzzySat and a standard SMT solver like C3. We tried a few naive approaches for concurrent execution, and there were no big positive impact. We learned a lot, so I believe this is just another confirmation that fuzzers and fuzzing is effective. Building symbolic expression it can be expensive, especially in concurrent execution where you do this at each round, but you can learn a lot from these expressions that you build. And GFS and FuzzySat are just the first steps in one direction, I believe. Recently, there was another project, Jigsaw, at IEEE Security and Privacy, and they were somehow engineering an approximate solver. They, I believe, had good results. So I think there is still something to do in this direction. And that's it. Thank you. If you have questions, I would be happy to answer them.